Welcome back. This is part 2 of chapter 1, discussing the human heart. So now we're going to talk about the complex structure that is the cardiac conduction system. And this is where we start understanding what it is that's happening when we look at an EKG rhythm. In its simplest form, we could break down the cardiac conduction system to these few units. And with normal physiology, a normal EKG rhythm, this is exactly how the conduction works. The pacemaker is the SA node. That's where things begin, right? That automaticity of the SA node. SA stands for sinoatrial node, sinoatrial. So you can guess where it lives. It's in the right atrium near the coronary sinus. So the sinoatrial node sets a rate. It's got an intrinsic rate of about 60 to 100 beats per minute. That's why that's your normal heart rate. Okay, so it starts at 60 to 100 beats per minute. The SA node fires or depolarizes, or however you want to think of it, starts the conduction wave. And then the internodal pathways take that wave of depolarization from cell to cell, all right, and depolarize the atria, all right? So you have your internodal pathways, you have Bachmann's bundle that takes the conduction from the right atrium to the left atrium, and you get conduction across both atria almost simultaneously because these pathways are fast. They're like highways of conduction. The AV node, it looks like a yield sign here because that's where things almost pause. I don't want to say pause as like an asystolic pause. It's a very brief pause, okay? And that's just enough time to allow the atria to eject all of its blood and the ventricles to optimize filling, okay? Because with the depolarization, you get cardiac contraction, right? You get the mechanical component. And that's what we're hoping is happening. With normal physiology, that's exactly what happens. So you have that brief pause at the AV node and blood fills the ventricles. And then the conduction goes down the AV node into the His bundle or AV bundle, as it's more commonly known now. And this is called the AV junction. The cells around the AV node and the His bundle or the AV bundle conduct and depolarize. And then the bundle branches, which take that conduction into each ventricle, right? You have your left bundle branch, which is made of 2 fascicles. And then you have your right bundle branch, which is a single fascicle. And then it ends with the Purkinje fibers, and the depolarization ends at the ventricles, and then repolarization. And then, of course, this happens again over and over to maintain a heart rate. Of course, it's important that we understand what's happening with the actual cell. And this is what happens with each myocyte, and there's a lot of them. Heart cells have 3 unique components that make their electrical function possible: automaticity, conductivity, and excitability. The flow of electricity through the heart is referred to as depolarization. That's why you've heard me mention that a couple times. This is because the cells change polarity from a negative to a positive state as potassium and sodium are actually exchanged inside and outside of the cell. Potassium is a dominant intracellular ion, meaning that there's a lot of potassium inside the cell, and sodium is the dominant extracellular ion, which means there's a lot of sodium outside of the cell in a normal state at rest. During depolarization, sodium rushes into the cell and potassium exits the cell. During repolarization, the cell uses its sodium-potassium pump to create the resting polarized state once again. So if you think of the way depolarization flows through the heart muscle, it is an attempt to stimulate contraction. Normally, the heart will contract due to this electrical stimulus, and it pumps blood to the lungs and to the body, as we know. However, it is possible to have electrically functioning heart that is not mechanically functioning. We call that pulseless electrical activity. Okay, so if you look here at the cell, you can see how it starts in this polarized state at rest over here, where mostly intracellularly it's negative, right? And it changes as sodium starts to come in and potassium starts to leave, and the cell becomes more positive and then more positive until it's fully depolarized. And then after depolarization, you have to have repolarization. And because now you have almost an equal amount of potassium inside and outside and an equal amount of sodium inside and outside, you have to use energy to pump the potassium back into the cell and pump the sodium out of the cell. And then you end up with that normal resting state again. So here's an image of the conduction system that we talked about. And what I'm going to do for you is I'm going to try to draw the heart here around it so you can imagine how this exists with the chambers. All right, so those will be our 4 chambers. So on this side is the right side, on this side is the left side. All right, so conduction, as we said, starts at the SA node. That's right here. And this would be a little bit more to the right side of the heart. But that's okay. You can get an understanding where it is where, where I said it is earlier. It's in the upper right side of the right atrium. That's our normal pacemaker. So the sinoatrial node sets the rate 60 to 100 usually. And then depolarization will continue down these intranodal pathways, and across what this is called Bachmann's bundle to the left atrium. And the reason for these pathways is because that's like the highways, the fast lanes of conduction. Whenever a conduction gets outside of the pathway, like if it was out here, it would still occur because all these myocytes have conductivity, but it would be a lot slower, right? So conduction is quicker when it happens in the conduction network. That's normal, our normal physiology, right? So then it gets down here to the AV node. The AV node actually sits somewhere like right around there, almost in between the right and left atrium. But that's okay. It pauses and allows for ventricular filling of blood, right? So we get that pause in conduction to allow for ventricular filling, and then it continues down the AV bundle, and then these bundle branches and the Purkinje fibers, and depolarizes the entire heart. So here's a better image with the heart already there and give you a better idea of what's happening. So again, try to think of the conduction as an independent thing. It's independent from the pumping of the heart, but it should cause the pumping of the heart. So the electricity or the electrical function and the mechanical function of the heart are 2 different things, but you hope that the electrical function is stimulating the mechanical function. Otherwise, you have death, right? All right, so SA node takes the signal or starts the signal, sets the pace. Conduction flows down these internodal pathways across Bachmann's bundle, and both atria are depolarized almost simultaneously, not quite simultaneously, almost simultaneously. Conduction stops at the AV node, allows for blood to flow down from the atria to the ventricles. Get good ventricular stretch. You want that Frank-Starling mechanism. The Frank-Starling mechanism is almost like a rubber band. The further you pull a rubber band back, then the farther it will fly, right? When you release it, same idea. The further you stretch these ventricles, the better your cardiac output. So we want more ventricular filling. We want better Frank-Starling mechanism. Conduction goes now from the AV node down to AV bundle. I know it says His bundle or bundle His in some texts. I said it earlier in this presentation. Now we're mostly calling it the AV bundle. So you might see both, but it's usually called the AV bundle now. And then these bundle branches, that's after the bifurcation, okay, right here. You have the bundle branches, and the depolarization will continue down. And the Purkinje fibers are interspersed in these ventricles, like everywhere in these ventricles. You have Purkinje fibers, and the ventricles just rapidly depolarize really fast, hopefully causing the ventricles to contract and blood to eject to the body and to the lungs. That brings us to an end of the second part. I'll see you in part 3 of chapter 1.